Hey guys, welcome back to .NET. Again, not a huge amount. I'm just going to readjust this, guys. Again, not a huge amount happening in the technology world this week. A few things to talk about though, but nothing like spectacular. Haven't bought anything this week, unlike last week where I had a new graphics card and camera. Just been trying to tidy up a little bit. Sort out the mess that is this shed. I did a little kind of vlog that I need to cut together and put out for you guys just to show you the kind of crap that I ended up doing. I spent all of yesterday and some of today just sorting stuff out, and then that's like a weekend gone basically. But anyway, let's talk about this. So a lot of you are probably aware or heard of Optane. It's something that came out in X270. It's kind of an Intel feature, if you like, but it goes along with our optane memory, which is this kind of 3D XPoint NAND memory, if you like. So essentially, it's just a faster version of what we have now, like TL NAND and things like that. It's quite interesting though. So it's PCIe Gen 3 times 2. M.2 compatible, and it's quite interesting. So it comes in 16 gigs or 32 gigs at the moment. But what's cool about this is it's basically layered. If you imagine what HBM2 is like for DDR4 memory or GDDR5 memory, Optane 3D XPoint is kind of like that in terms of NAND TL flash. It's just stacking them up with interconnects to reduce the latency in both read-writes. And it's quite interesting. There's some people have looked at it. Linus looked at it. Not sure if I see the point of this until they scale it up into large drives. I think you can buy an enterprise version drive of this at the moment. But I think they were talking about something like it has 100 times less latency than a NAND, but it's still sort of 10 times or 20 times slower than DDR4 than memory is, but it's permanent unlike DDR4 SD-RAM. So essentially, I think the way Intel has been kind of selling this is you buy one of these little chips. Just looks like an M.2 chip. In fact, there it is, an M.2 drive. You can get it in 16 or 32 gigs. Only works on Intel Optane optimized boards or enabled boards, so X270 I think, which is kind of annoying for people like me who are on Broadwell E and stuff like that, who might want to take advantage of this. But essentially, all this does is you put it in and it acts like a faster kind of caching system, if you want, between your hard drive and your SD-RAM. So in the same way that people used to use SSDs back in the day when they came out, when you got those really pointless kind of 32 gig drives, if you had a hard drive and you just had SD-RAM, you would buy one of these 32 gig drives and stick it in, and you would essentially just use it as cache, so that the first time you boot, you probably wouldn't see any benefit at all. But then once the drive and the software became more optimized through booting and what you're going to load and things like that, so realize what you were doing, then your boot times would come down, etc., etc. So that's essentially what Optane is at the moment. Linus did a video about this. I think Wendell did a video about this as well, where there is an improvement in boot times, but again, there's only an improvement if you're not already booting from an SSD. So the use case for this, I don't really see the use case for this at the moment in the consumer market. Because most people building a PC now, they have at least 2 drives in their machine. They have a boot drive for an SSD boot drive, and they have a mechanical drive for mass storage. So I can't see where this device is going to fit into the market. I might be completely wrong. There might be some enthusiasts out there that are really, really interested in this kind of thing, but certainly at the moment, I'm just not that bothered about it. and it is cool. Like, the technology is very cool, but like I said, the technology will be much cooler. Here we go. Yeah. So yes. So basically, it's in between memory, so DRAM and NAND SSD. So yeah, it's basically got 100 times the latency of DRAM, but 1,000 times the storage. So it's quite interesting. It's an interesting concept. It's been done before. Like I said, it was done before with SSDs when they first came out. Yeah, I don't know how much these cost. I can't imagine they're very cheap at the moment. Again, for someone like me, I wouldn't even. I am an enthusiast, and I wouldn't buy this. I don't see the point in it. I don't think I'm going to get much benefit from it. In the enterprise space, though, if you can get like a 240 gigabyte drive version of this to boot from, I think it probably would make a massive difference in terms of latency between your operating system and memory, especially if you're doing large computational tasks and things like that, and you need to move large data chunks around quickly. Then yeah, I can see it making a difference. But for people like myself, no, not really. To be honest, I don't even see the point in getting an M.2. I don't have an M.2 drive. I would like one, but I don't have a burning passion to have one because all the analysis I've seen out there, it's not really worth it. I don't think you get a huge benefit from having it in game load times and things like that. I think the only benefit you get from having something like an M.2 drive is if you're moving massive files about. So if you had an M.2 drive that you're just using as a scratch drive in something like Premiere Pro or After Effects, for instance, DaVinci Resolve, so something like that where you're moving huge files about, I think, yes, you would get a benefit. But anyway, cool technology, really, really cool technology. And now we're going to move on to some other cool technology. So this is some researchers in MIT have found a more efficient process at building chips below 10 nanometers. So currently, I don't know how many of you are kind of up on lithography and how they actually make CPUs and things like that. But essentially, they etch. It's like they etch a pattern. Lithography. They etch a pattern into the silicon. With various mediums. That technology has been around for a very long, long time. However, currently they are reaching. Pardon me. They're reaching the limitations with extreme ultraviolet wavelengths. So again, I don't want to wait. So the wavelength of something determines how small you can actually etch into the silicon itself. So if you've got something with a 14 nanometer wavelength, then you can't make anything smaller than 14 nanometers, if you see what I mean. So I think they're getting to the kind of extreme end of the ultraviolet wavelength that is still affordable to actually control in a manufacturing process. So TSMC and things that people like that have talked about this, and they're saying, that's the difficulty they're having in getting to 7 nanometers with decent yields. So these guys these guys at MIT have come up with a completely different technique. So I need to read it off my other screen. It's not large enough on this one, or maybe I can, guys. So it's basically called direct self-assembly, or DSA. And in DSA, what they do is they build up a number of layers rather than just using one wavelength, so one ultraviolet wavelength to etch that pattern, if you like, that CPU pattern into the silicon. So what they'll do is they initially, in the same way they do now, they might use something like an electron beam to print the chip's basic pattern. And then the second step would be laying on some form of polymer on top of that, sort of so it would give it height, if you see what I mean, on top of that print. So then you effectively got two prints, and then on top of that you can lay another copolymer layer which could go in another direction or go in the same direction, and then on top of that you can use or you can lay a separate kind of protective layer using a chemical vapor deposition. So it's really, really cool, because then you get you get your vertical stratification like this, but you know, you can have like the initial lithography can be going that way, all in this way, and then you can have another layer which might be for interconnects and things like that. And then you can have another layer on top of that which could be for interconnects. So you can see how you could scale quite complex designs using this technology. Very, very exciting. This is probably more exciting to me than a lot of things that are happening currently. People tend to get very excited about graphics cards and things like that, whereas I think this is more interesting. It's kind of what we do where I work. Kind of the theory is the same. This is a lot more high tech than what we're doing at work, but we dabbled with things like this in what we manufacture, and it's quite cool. Ours is on a much kind of macro scale compared to this. This is tiny. We're working kind of plus. I think the smallest we go down to is the micron scale, so nowhere near the same kind of scale these guys are working, the minuteness of it. But this is really, really exciting stuff, guys. So I mean, essentially it's doing the same thing they're doing now. It's just using a different technique. So for instance, if you can use an electron beam, you can easily get below 7 nanometers using an electron beam. Pardon me, to lay out that initial lithography step. And then if you have, I don't know, at the moment I think they've only done 4 layers. So they've only done the initial layer, the 2 copolymers, and then a sealing layer. But I don't think there's anything to stop you having more than 1 copolymer layer, so that, again, like I said, you can have that initial kind of base print of the die area, and then you build the vertical height, if you like, of the transistors or interconnects using these copolymers in various directions. So very, very exciting stuff from MIT. Very exciting, much more exciting than this, for instance. Although Optane's quite exciting, but it's kind of it's an iteration, if you like, on a current process. You know, HBM, this is not that far removed from HBM2 in terms of theory. In terms of manufacturer, it's probably not that far removed either, I wouldn't have thought. I think did Intel develop this with Micron? I can't remember. They do have a development partner. I'm not sure if they talk about that in my partner in this article. No, I don't think they do. Anyway, the Optane's pretty cool. But this is much more interesting. Direct self-assembly, very, very cool stuff. So yeah, this is what they're talking about. So this will be a chip or lithography made using direct self-assembly. It's very, very cool. So you can see the different layers that have been built up vertically. I'm assuming this is Y and not X, if you see it in terms of, or yeah, Y, not X, and then Z would be coming out of the screen in terms of axes. Very cool stuff, guys. Moving on, this is the only thing I could really find about Ryzen at the moment. Apart from the only thing I actually want to know about Ryzen currently is when it's going to be available for pre-order, so I can pre-order my Ryzen 1600 chip, which I really, really want. So, and I'm going to get a B350 motherboard. I'm going to go really like budget build with this Ryzen system, guys, and see. I kind of reckon I'll spend maybe £400 between the CPU, memory, motherboard. I already have a graphics card in a case. So I just want to see what you can get for like 400 quid in terms of performance versus my Broadwell E system, where the motherboard, the memory, and the chip was like £800. It's basically double. So I'm interested in that kind of comparison. But yeah, That's what I'm interested in terms of Ryzen. However, this is reasonably interesting. So Ashes of the Singularity has been officially, it has been optimized for Ryzen. I don't know what that means in terms of optimized, but you get a bump. So with a bit of optimization, I don't know what that optimization is. Whether it's like, I mean, it's not going to be a complete recode, but from the way WCCF Tech are writing here, it sounds like a fairly substantial, like more than a patch. And you're seeing, depending on where you look, you're seeing between 16 to 28% improvement, which is pretty cool. You knew, right? Yeah, so it's looking better. DirectX 12. Results calculation. Ryzen. Here we go. Ah, yeah. And then they're talking about Ryzen processors need optimized code for every game to run at full potential. I don't agree with this. I think yeah, I think this is a bit misleading. Where they go on to talk about if you want to achieve Intel-like performance, Ryzen processors, then it means that the underlying problem isn't being solved, but is rather being worked around, hence the patch or optimization. This would further imply that the problem isn't something which can be fixed with a magical software patch, but rather something has to do with how AMD has implemented SMT in a new architecture. I don't agree with that, because essentially this whole article is about a game that's been optimized. So they've optimized Ashes of the Singularity. I'm sure they haven't optimized it just for Ryzen, because if you look at this chart, they're talking about Ashes of the Singularity escalation, CPU test, DirectX 12, crazy preset. So new, old, new, old. So it's not just Ryzen that's getting a bump from this, and the Intel system is also getting a bump. So I don't know if this is so much an article talking about Ryzen, a game being optimized for Ryzen, or just a game that's been optimized for DirectX 12. Because I don't know if Ashes of the Singularity is actually being coded for DirectX 12, or if, like most games, it's a DX11 title with a DX12 wrapper. So essentially DX11 is doing everything, but then you've just got another layer of abstraction, where instead of DX11 doing the calls to the CPU, etc., there's that extra layer of kind of nonsense where DX11 engages and then it sends a message and DX12 intercepts it, and then they're saying it's DirectX 12. So unless they've done something to kind of remove that overhead between DX11 and DX12, or if they really optimized it, I don't know. I just know that I don't agree with this statement, because all games are optimized. I mean, I recently got Ghost Recon. When I got my 1070, I got Ghost Recon, and I've got a 6800K at 4.5 gigahertz, 32 gigs of RAM, a 1070 overclocked 2.1 gigahertz, and I was playing it at 1080 on Ultra just to see what kind of frame rate I would get, and man, I was getting like 50 frames a second, 55 frames a second, and I was just like, this is bullshit. And that's just because it's unoptimized. It's an unoptimized game. The bit of software has to be optimized. It has bugs in it, and it'll have inefficiencies, and it'll have extra overhead, etc., etc. And I see that in an Intel system, and I'm pretty sure people who are running Ryzen are having the same problems. So once that game is then optimized, both systems will improve. So I don't think it's got anything to do with Ryzen's architecture per se. It's why the WCCF Tech are starting to. They were getting better for a good while, I thought, and now I'm just kind of stuff like this, just sweeping comments. Unless I'm missing the point of the article, but it seems pretty clear when you read through it, and then that this is all to do with Ashes of the Singularity has been optimized for Ryzen. It doesn't tell you what that optimization is or what they've done. And then here they start talking about everything will have to be optimized for Ryzen, and blah 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 blah. A software patch isn't going to fix it. And it's like, well, a software patch is what's made Ashes of the Singularity better. How else are they going to optimize it? They haven't sent a microcode update to everyone's CPU. You know, they've patched the game. Unless they've re-released the game, I don't think they have. So confusing. I need to look into this more. But yeah, WCCF Tech, get a grip. Kind of. I suppose it's a headline. If they published graphs that were just flat, no one would read them. But yeah. Anyway, kind of moving on from that and staying in the same vein, because there's something I want to talk about at the end. And Antec did a quick look comparing Vulkan and DirectX 12 API overhead and 3D Mark. Now this is really interesting, actually. I'm not going to bother you. If you guys want to read this, you can go through it and read it. But essentially, they're testing the APIs on 3D Mark. So what's the maximum number of draw calls it can do, essentially. So all these were done on the same system. And this was published not that long ago. Interesting that they're using a 4960X at 4.2 gigahertz. An SSD, yeah, so it's all good stuff. And then they've got a GTX 1080 Ti, 1060, and an AMD RX 480. These are all kind of, NVIDIA cards or Founders Edition, and the Radeon RX 480 is pardon me guys, is a bog standard off-the-shelf garden variety from AMD. It's not an aftermarket board. So, we look here at these graphs. These are quite interesting. So, this is 3D Mark API overhead feature test, 1060. So, Vulkan, 26.4 million calls. DirectX 12, 20 million calls. And DirectX 11 multi-threaded and DirectX 11 single-threaded, pretty much the same. So, it's quite interesting stuff. So it's quite interesting that Vulkan seems to have a much lower overhead on the 1060 than DirectX 12 does. Not sure what that relates to. But it's basically a 32% difference between what it can call on Vulkan and what it can call on DX12, which is quite interesting. There's obviously a bottleneck in there somewhere. Because moving down, when you get to the RX 480, so on Vulkan it can do 24.9 million, DirectX 12 can do 26 million, DirectX 11 and multi-thread and single thread basically the same. There's no difference. So basically, on the RX 480, there doesn't seem to be a huge amount of difference in terms of overhead between Vulkan and DX12. I would say, anyway, when you compare the red and the black bar there to the red and the black bar here, that's a massive difference. Whereas here, it's probably, just trying to figure it out in my head, divided by 10, 2.6. It's going to be less than 10% different, maybe like 7% different there. So it's not that bad, really. And if you reran this test probably 100 times, that difference would probably come down, I would think. So, like, I can't imagine it's going to get any worse, whereas this would bounce about a bit more. I think that's more real. I still don't get why it's like that on a 1060. But yeah, it's very interesting the RX 480 is looking pretty solid no matter what API it's running, apart from DX11. Blah 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 blah. Better, yeah, exactly. So, and this is the interesting one as well, like 1080. So GTX 1080. So Vulkan, 32.4 million on DirectX 12, 31.3 million calls, and again, DX11 multi-threaded and single-threaded are pretty much the same. So this is pretty interesting. So, that's nothing. There's going to be a couple of % difference on the 1080, which is really good again. So Vulkan pulling ahead a little bit and DX12 falling behind a little bit. But what's interesting about all three of these cards is Vulkan does seem to be better on the NVIDIA side. I don't get that, why that would be as an API. I mean, that's marginal here. I mean, actually, to be fair, I would call those the same. I would say there's no difference on the 1080. The 1060, there's a difference for some reason, but I think the takeaway for me for this is that in terms of this very small test, like this very specific test, the APIs are much better. The new APIs like Vulkan and DirectX 12 are much better than DX11. And also I'm very happy that there's not much difference between Team Red and Team Green, which is really good for consumers. So yeah, we need to start using DirectX 12 and DirectX and Vulkan, basically. Developers need to move away from DirectX 11 and not, and when I say use DirectX 12, I don't mean we put a DirectX 12 wrapper on a DirectX 11 game. That's not what I mean. I mean we need to move over. The system needs to change. And I know that's easier said than done, but I do have a bit of kind of pity for developers. I know a few guys who are coders, and I know it's easier said than done. Like, you know, ask a programmer to program anything that has like leap years and leap seconds in it, and they'll hate you. They don't like it. And then leading on from this, there's not really much, I can't talk about this. What I would like to do is tell you all to go and watch this video, Ryzen of the Tomb Raider by Adored TV. Now, this is a fantastic video. Recently, Adored TV took a bit of flack from other tech tubers, largely because he does his own thing. He does his research, and he's very fair. He's not a fanboy, and he's not part of a tech tuber clique. Like I've noticed that tech tubers are tending to kind of clique together now. So they've got their little support groups, the bigger channels. You know, like you've got the Aussie block currently. Got the you know, you've got like Tech City. Oh, they should have left it at Tech Yes City. You got Tech City, you got Tech Showdown, and you've got Hardware Unboxed, who've all kind of banded together in the southern part of the world there, and they share all their benchmarks together. And I'm sure, like, I like them. I watch a lot of their stuff, but my God, don't ever criticize them. They'll all be on your back, basically. And then in the States as well, you've got like Bitwit, Paul's Hardware, people like that who kind of band together. Jace 2 Cents, they're always on each other's channels. So you get these little cliques forming, and what I like about Adored TV is he isn't involved in any of that, which is really good. I'm also really glad that his sub count's going up. I think he's at like 45,000 nearly. When I started watching this guy, he had like 8,000 subs or something. So it's a while ago, but his videos are really, really good. So I would advise you to go away and watch this. And he talks about API overhead, essentially, on Ryzen, where he looks at NVIDIA and AMD cards. But he looks at Vulkan and DirectX 12 in a very different way. So he looks at it, instead of doing like a draw call test where it's not the same kind of load that a game has. So if you think about a game, you know, a game has generally one thread load, and so within that thread, there's lots of stuff for an API to do in that one thread. So that's when you know you can get a CPU bottleneck, etc. So he looks at it in terms of that, where he looks at Rise of the Tomb Raider, because a lot of people had a lot of problems with that benchmark on DX12 on both cards, on an NVIDIA card and on an AMD card. And so what DirectX 12 should do is take that thread in a single threaded game scenario, and it should break it up across the CPU so that you're never going to get into a bottleneck scenario, unlike the test that we just looked at on an Antec, where it's basically draw calls from the GPU. So it's testing the GPU's ability, not the CPU. So whereas games are both. So this is a great video. and it's really worth watching. It's quite long. It's worth watching the entire thing. It's very, very good. He comes up with a lot of good points. He puts a lot of criticism I think he's faced unfairly to bed. And there's also a really interesting point at the end where it looks like DirectX 12 is actually just really badly implemented on NVIDIA graphics cards compared to AMD cards, which I never thought I would say, but from his testing, it's quite interesting to look at it. But yeah, I would advise you to go and look at this video, guys. It's really, really good. And that's it, guys. It's finishing on a kind of a... I don't usually plug people like this, but it's a really good video. You should go and watch it. But that's me done, guys. So if you've got any questions, fire them in the comments right now. I will stick around for a couple of minutes as always. And as always, thank you very much for tuning in. Had a bit more time this weekend. Got some more stuff sorted out, so the news was a bit more newsworthy. But not looking forward to later in the year when the whole GPU cycle starts up again, and that's all people are going to be talking about. And it's quite hard actually doing this every week because there's not a lot of stuff happens really. Apart from when things are building up to launch, you know, like the RX 5 series cards, or that's nothing interesting. Vega will be interesting, but again, I'm kind of almost bored of Vega because it's been going on for so long. It's kind of a bit like Ryzen. By the end of it, I was just so fed up with people talking about Ryzen, I couldn't really be bothered anymore. So at the moment, I'm kind of going through a bit of a melancholic spell just because not a lot's happening. Or, you know, you go on YouTube or an Antec and these things, and there seems to be loads of news, but it's just kind of like, well, it's nothing really new. But yeah, that's just me being grumpy, Scottish and grumpy. So guys, if you don't have any questions, I'm gonna get on out here tonight. And again, thank you very much for tuning in. Looking forward to getting my Ryzen build on the go. Possibly not at launch. I don't know if it'll be sold out or not, which is why I want to pre-order a chip. But it'll be happening in April anyway. I've got a few other things to buy as well. And that's really it, guys. Thanks again. Enjoy the rest of your Sunday evening. I know I'm going to. Take it easy, guys, and I will catch you later. Bye.